Now I would like to welcome to our meeting Aishwarya. Aishwarya is a data scientist at Episource LLC with 2 years of experience around building machine learning and data-driven solutions that provide inference on healthcare data. She is now delivering and maintaining end-to-end ML solutions. So I'm just going to pass it to you, Aishwarya. Thank you very much for being here.
Thank you for inviting me here. I'm going to talking about the interpretable ML models at scale. So I am Aishwarya Agrawal and I am working as a data scientist at Episource LLC. I am a first-time speaker. Feels great to be here and very lovely to meet all of you. I love to build machine learning and data-driven solutions. So I have been in this field for last 2 to 3 years now, and now I am building and maintaining end-to-end ML solutions. You can reach me out on our LinkedIn or you can reach me out on Twitter. Anywhere is fine. So, little about my company. So, I am right now working at Episource LLC. It is a healthcare company that provides healthcare that works on healthcare data and analytics and provides solutions for risk adjustments and quality solutions. We at Episource also have a machine learning and NLP platform that serves a wide variety of ML problems. And we have currently like 15 to 16 ML models in productions, which are used for a variety of use cases. On some of those I work, and some my team works as well. So yeah, the data is huge, and yeah, we are serving healthcare and the solutions using machine learning. Today my topic is interpretable ML models at scale. So I'll be going over the agenda if it is visible. Yeah. So in this talk, I will be taking you through the thought process involved in systems design, the application, and importance of designing an ML system. The first part, like, if, I think there is a brief context here. I mean, we need to understand how an ML model works and why do we build an ML model. So my agenda is like this. I'll be defining what interpretable ML models are, how you can build a self-service interpretable system, how you can optimize these systems for scale, and what are the perks that comes with an interpretable system. So yeah, this is my agenda. So moving on to defining interpretable ML. I think yeah. So in every machine learning system, what we usually do is we given some set of features, and then we get out a prediction. It can be a probability, it can be a regression between these numbers, it can be portfolio. But interpretability machine learning is understanding like why we have predicted a given thing, why we have classified in a cat versus dog problem, why we have classified this as a cat, or when we are talking in healthcare, what we are trying to do is, if, for example, if we have an ML model that predicts the likelihood of a patient getting diabetes, then I want to know why the patient is getting diabetes, so that I can recommend later what are the lifestyle changes that the patient can make in their life. Now, what interpretability here will be doing is it will be telling us why the patient has been suspected with diabetes. Now, this may be because of his high A1C levels, it may be because the microalbumin is high. There can be a variety of reasons in our feature set that was given, and because of which the patient might have diabetes. So in this particular scenario, we can't go around and just say that patient is patient has getting diabetes, but we also need to explain that why do the patient will have diabetes. So interpretability is basically determining the cause and the effect. It is the degree in which a model can be understood in human terms. Uh, yeah, so I hope you understood what I mean by interpretable ML. Like this is a slightly different from explainability. So in explainability, we give out feature importance of the thing, but in interpretability, what we do is we try to make this as as humanly understandable as possible. We try to keep things simple, so that anyone who is taking or who is looking at our predictions can understand that why we have made that particular prediction. There is a quote by Albert Einstein, like if you can't explain it simply, then you don't understand it well enough. I think in machine learning, when we are talking about model interpretability, the end goal is to make our predictions explanations so simple that anyone can understand it. From this quote, I would like to take it another way. Like, you have to explain it so simply that anyone can understand it well enough. Simply following the LE5 or even a 5-year-old can understand principle. So whenever we are interpreting a model or whenever we are interpreting a prediction, the explanation should be so simple that anyone can understand that. So that was the major drive behind us building this solution, building the entire system around this. And next, I'll be explaining about how and why did we build a self-service interpretable system and what I mean by a self-service interpretable system. So um, building a self-service interpretable system, I'll be talking about the problem and the solution. So before going into how did we build a self-service interpretable system, I would like to bring some context on why did we need to do it. See, with ML models built on domains where we have heavy compliance, stakeholders lean to us for explanation for every prediction. In fact, these type of systems help us to learn from the models. Sometimes machine learning can even help us in discovering patterns in our data that we didn't even know existed. But the thing with some ML models can be that we can't just understand these patterns from the predictions themselves, but when we gain visibility over the importance of the features and how they are being derived from the data, then we can make out relationships of the data and understand what are the patterns in the data, and maybe we can later work on a system that improves all these things. Um, so taking my previous example, so we have created a model that predicts likelihood of a disease for a patient. Now we want to automate this model. We want to automate and make suggestions to the patient about some lifestyle changes. Now, before going to the patient, my boss will be asking me, what are the details? How are you going to explain to the patient that he is going to have that particular disease so that the healthcare provider somewhere else can suggest those lifestyle changes? In these kind of situations, we need to give them the explanation, like why I am saying that you are going to have this particular disease, or why my model is saying that there is a very high probability that you are going to suffer from diabetes. So, for such reasons, the first being that the stakeholders asking for our explanations for every prediction, the client itself asking for the explanation itself, and for building the trust itself, we decided to build a self-service platform that stakeholders and anyone dealing for explanations for predictions can use to understand why we are predicting and what we are predicting. And when we give them the explanations, these are in a summarized manner and in an understandable fashion. And we are not just going to give them the explanation in like the feature importance format, but we give them like the top 5 explanations in a template so that they can understand, and they don't have too much information, but we do not have too much information. We do not have too less information either. They understand what is the cause and effect there. So these numbers tend to give them an understanding of how the system is working behind the scenes and overall making them understand our ML models and maybe gain a credibility there, like the ML model is working fine and correct on the correct data. Uh, in this talk, I will be talking about different learnings that we got after building the interpretable systems for different use cases. Some of the use cases were how we built n different models and then integrated the interpretable part there, and how did we scale out the system to meet the SLAs. So first, I will be talking about the problem. So the problem statement was like this. So we have to explain every prediction. Second, we have to predict and explain for 1 million rows in an hour. We have to give summarized explanations from n models to stakeholders. And then we have to take feedback from the stakeholders, like if the prediction and the explanations match, if the model is taking correct features into account for the prediction itself. So in these four, I can summarize what my problem statement was. Now I will be talking about the solution. So was the major design decision that we took here was we chose GBTs over neural nets. So GBTs are gradient boosting trees, and we decided to go with some GBT-based model over neural nets, and the major reason for that is its interpretability. Although many techniques are available now to explain neural nets and everything else as well, but still, with the other techniques, overall speed of processing becomes a major bottleneck for us. So for this use case, we were working on tabular data set, and when after multiple experiments that we did, GBTs did outperform our neural networks. So that was a plus point for us there. So we went with GBTs. Second, we use Shapley values for feature importance. So Shapley values works on a game theory, Bayesian game theory, and these tell us how to fairly distribute the payout among the features. They tell us how important each feature is and how each feature is contributing to the prediction itself. So these values help us understand which features to take, which features are important, which features are positively affecting the prediction, and which features are negatively affecting the predictions, so that we can give out the most important features in the summarized explanation part. Uh, after the overall Shapley values, we used we generated the most important ones, like the top five, and then used those to generate a summary. After that, to manage the scale of the data, we use celery task queues for distributing distributed processing. So we divided the entire data in batches and then distributed it across different instances and across different cores, so that we can utilize all of the computing resources that we have and get the results in time. For data dashboard part, for showing it to the stakeholders, we used Streamlit. So when we processed everything and it went to the backend, we developed a Streamlit-based dashboard that the stakeholders can use to understand, okay, this is the prediction and this is the prediction explanation. So they don't have to go through files and everything, but they can just pick and drop and select over there, like, okay, this is going to be if I'm going to give in this member's data, then this is the prediction, and this is why I'm predicting this. So this makes it very easier for them to understand and to access. Last, we provided summarized explanation of predictions. So we gave them top five major game changers for the prediction. We fit those in the template and provide summarize instead of providing them tons of features and the feature importances that they don't care about really. I mean, they only want to see what were the top factors that were important and what the top factors which are making out the prediction, right? So yeah, these were the major libraries that we used. We used CatBoost, we used Streamlit for data dashboards, we used sharp values, the feature importances, to understand, to determine which features were important and how much they were contributing, so that we can explain those later. And we use celery-based distributed processing. So this was our solution. We combined all these things and then put it out on scale. So next, I will be talking about the optimizing part. So how did we optimize the entire thing for scale? So first of all, we immediately switched to Parquet. Major reason for using Parquet was um, because the entire thing is very computationally expensive, and Parquet has a major advantages on high execution speeds, faster I/O operations, and it consumes very less disk storage. And apart from this, this is very easily pluggable to other data dashboards as well. Apart from cited, we can plug it to Athena as well, and we can get our data in the dashboard. So here I'll be talking about the various steps we took to optimize overall process along, apart from the key design decisions that we take, like after adding explanations for every scale. Since it is a very time consume, very compute intensive process, the prediction explanation part, you can get predictions in the given SLE very easily. But since sharp values calculation is based on game theory, it is very computationally extensive. So if you are working with a very unoptimized code base, it will become impossible to meet the SLAs. So it is absolutely necessary to optimize every bit of your code base, so that the only thing that is remaining that is taking the time is your sharp. Other than that, everything else is optimized. We profiled the entire code base. We took out chunks of functions and we understood, okay, what is taking the most, what is taking the most time, and we optimized every bit and piece of it so that the last remaining thing was sharp. After we did that, we what we did was we converted our data in batches. So what we did, we benchmarked the data batch. So we took out the system, we selected an instance and saw what batch size works best for this particular instance. And then we broke our data in those batches and then sent those out for distributed processing. One more thing that we did here was we branched out the predictions and the prediction explanation. See, prediction does not take that much time, but prediction explanation was taking a lot of time for us. So what we did was, to provide fast predictions, we branched this out. First, we provided the prediction to the end user, and later, in some more time, some half an hour or more, you can get the prediction explanation as well. So predictions are immediately available, and in some more time, you can get the prediction explanation. Lastly, we auto-scale the instances based on the input size. So since distributed processing was involved, celery workers were involved, we had a master slave architecture where the batches were distributed across different cores and instances, and how many instances to launch and how to scale was dependent upon the input size that was given to us. So suppose if 1 million rows are there and the batch size is 100, then we launched our instances with respect to that. Yeah, so this is how we optimized for scale and met our SLA. We processed roughly 1.1, more than 1 million rows in under an hour with predictions and explanations across 80 different ML models. So lastly, I will be talking about the perks that come with interpretable ML. So yeah, with interpretable ML, since we get all the predictions and explanations and everything else, we can we can early detect the data drift. If they How can we detect it? We can see that if the most important features are changed for a given prediction, yes, something is wrong there. I mean, um, because of diabetes, if the insulin value is not taken into consideration, then there is definitely something wrong with this. So yeah, we can detect how the features are changing and which features are not important anymore, and We can take that into account to understand, okay, my model is drifting now. These systems also give us a sense check and give us an opportunity to fix errors. Um, with feedback loop incorporated, the SMEs or anyone verifying the predictions inspiration can help us in predicting for the right reasons. With multiple people involved here, with B getting the feedback for the ML systems, we can continuously improve our ML systems and predict for the right reasons. Along with feedback, these systems also help us in our AutoML workflows. So normally when we incorporate AutoML workflow, we tend to train the model on certain data after doing some basic sanity checks on the data. But with feedback system incorporated, we get a better sense of understanding where our model is lacking, on what type of data should we include more. Um, as mentioned earlier, since our system was since our system is, or since our domain is very compliance heavy, we have to follow compliance and we have to do everything in our power to make sure that we are predicting correct and we are giving the right reasons. The prediction explanation part becomes very important for us. These type of system also help us in gaining the trust on our ML system. When we are predicting things for the right reasons, it removes the much occurred fear or doubt or uncertainty and uneasiness that stakeholders feel because of some ML systems that, okay, why are you predicting this? We can tell them that we are predicting this because of these particular reasons. Yeah, so these were the perks with interpretable ML. Lastly, I will be talking about the key takeaways that we got after building such a system. So we majorly got to understand what were the trade-offs between explainability and performance. So like, okay, in our case, GBTs worked better for us, but sometimes what happens is your neural network can outperform GBTs or any other more interpretable system. In that case, it is very much important to understand what is the thing that you want to let go. Do you want performance or do you want the explainability part? Because if explainability is very important to you, then choosing the right factors and choosing the right designs is very important. Second, use Parquet. Parquet is very lightweight and the entire file processing was very smooth when you are dealing with tabular data itself. Third, optimize as much as you can. So like we did, we optimized everything in our functions. We optimized every bit piece of code. Fourth, it would be to keep it simple. Even if you're explaining something, don't overwhelm the stakeholders, just give them very simple information. And lastly, feedback makes an ML model even better. So yeah, that was my take on how we did interpretable ML models at scale. Um, and I am open to questions now.
Okay, thank you very much. Let's check over here in the Q&A. There's nothing in the Q&A. And let's check here. Do you handle feedback manually? Here's a question from Rishika. Do you handle feedback manually, or is there an automated system that incorporates the feedback in improving the AutoML workflow?
So yeah, for now, we are handling the feedback manually, but to automate the process, it is already in the designs and we will be doing that very soon.
There's one question from Ian. What was the biggest business win with interpretability? Was it to gain trust of stakeholders or to find errors?
I think both will be equally important for us. I mean, stakeholders definitely believed in us more. And with compliance in play, I think it was compulsory for us. I won't say even it was about trust, but it was a compulsory thing. Like we have to have explanations for our predictions.
And there is another question. What was the, from Sai, sorry. What was the hardest thing for you while building this system?
So the scaling part, I think, because when you introduce the Shapley values and all the computer extensive processes in between, the optimization itself becomes very difficult because you can optimize everything, but that particular part is always going to be computer intensive. So distributing across different things and then scaling in and out was was a challenge for us, but we did overcome that.
I think we can just wrap up and said that if anyone else have any other question, please reach out to Aishwarya through the LinkedIn or the Gather Town. So I just want to thank you again for your talk and also for being part of PyData Global 2021. Thank you very much. Really interesting talk, and thank you to all our attendees as well for being here.
Yeah,
So
thank you for having me here.